Welcome to my talk about steel decks with embossments and indentations. I am Anna Palisson. I am a consultant engineer and I offer consultancy services to develop steel cold form sections and structures as well as composite slabs in accordance with the Euro codes. I am presenting here the calculation method as developed within the GRISP project for steel decks with embossments and indentations. After a brief introduction to the topic, I am going to present the state of the art before the GRISP project in order to help you understand why the present methodology was developed. I am also going to describe the huge test program which was performed in order to provide the required data as well as provide the results of the testing analysis. Then, I am going to explain the methodology to calculate the effective section and the resistances of a steel deck with embossments and indentations. This methodology is proposed as an amendment on Eurocode 313. Lastly, I am going to introduce the Excel files which were implemented to calculate span moment resistance and support reaction and moment reaction interaction at internal support for a steel deck with embossments and indentations. Let me introduce the topic of this talk. On this picture, we can see a composite slab with concrete and with steel deck with embossments and indentations. Such composite slabs are frequently used in steel frame constructions, in residential, commercial and industrial constructions, as well for new constructions as for refurbishments. In order to increase the shear connection between steel and concrete, the webs of steel deck are equipped with embossments and indentations. At the composite stage, where the concrete and the steel collaborate, steel sheeting with embossments and indentations are within the scope of the standard Eurocode 411 for the design of composite structures. But at the construction stage, where the sheeting is used as shuttering and has to support fresh concrete weight and construction loads, no existing study allows to calculate the resistance of steel profile with embossments and indentations. The Eurocode 313 only deals with steel profiles without embossments and indentations. Therefore, the only way to design such profiles is to perform testing according to Eurocode 313, but these tests are expensive and time-consuming. Thus, at the beginning of the GRISP project, we could observe that despite the frequent use of steel decks with embossments and indentation, no information is given by Eurocodes or by literature on how to design them. So we could confirm that there was a real lack of data and relevant knowledge on how to design a steel deck with embossments and indentation, and that an innovative methodology was necessary. The state of the art has allowed us to determine the GRISP project objectives and the methodology to be applied to achieve them. The main goals were to determine the technical missing data and, of course, a calculation method for steel decks with embossments and indentations. The methodology consisted in determining the missing data by performing a huge testing program and then to define a calculation method based and validated on the analysis of the test results. This methodology was proposed as an amendment on the Eurocode 313. Now let's discover the extensive testing program which was performed within the GRISP project. The first aim was to determine the influence of indentations on local behavior. The second aim was to determine the resistance values of different types of profile that we can see on the pictures. The tests were performed on profiles without and with embossments and indentations. The third aim was to compare the values obtained for profiles without embossments and indentations with values for those with embossments and indentations. The fourth aim was to assess the impact of embossments and indentations, and the final aim was to define a calculation method for profiles with embossments and indentations. Now let's look at local testing. Tensile testing were performed on samples without indentations and on samples with indentations. Concerning the global testing, single span tests and support tests and internal support tests were performed according to the Eurocode 313 Annex A. Now look at the local testing results. On this graph, we can see that the indentations decrease the stress. The higher the indentation, the more the stress decreases. And now look at the global testing results. Here we can see the pictures taken during the single span testing. On the left, we have the test setup. In the middle, a profile without embossments indentations. On the right, a profile with embossments indentations. The observed failure mode for all the profiles was buckling of the upper flanges near the midspan. The moment resistance was determined. Here we can see the pictures taken during the end support testing. On the left, we have the test setup. In the middle, a profile without embossments indentations. On the right, a profile with embossments indentations. The failure mode observed for all the profiles was web crippling. The resistance at end support was determined. Here we can see the pictures taken during the intermediate support testing. On the left we have the test setup, in the middle a profile without embossments indentations, on the right a profile with embossments indentations. The observed failure mode for all the profiles was web crippling due to reaction and web and compressed flange buckling due to flexion moment. The resistance to combined moment and support reaction was determined. The results obtained for profiles without and with embossments and indentations allowed us to make comparisons and allowed to assess the impact on the structural behavior. The major results were that embossments and indentation decrease the moment resistance and increase the reaction resistance. The moment reaction interaction was increased for smaller span as it is governed by reaction resistance and decreased for bigger span as it is governed by moment resistance. A detailed analysis of the local testing has led to a reduced thickness equal to thickness multiplied by a ratio ρ, depending on the height of indentations and on the thickness. The next step in our scientific process was to come up with a calculation method for moment resistance, web crippling resistance, and moment resistance interaction. For profiles without embossments indentations, resistance were calculated according to Eurocode 313. For profiles with embossments indentations, resistances were calculated with Eurocode 313, but by considering the embossments indentations as flat elements with a reduced thickness equal to ratio ρ multiplied by thickness, where ρ is defined as a function of the height of the embossment's indentations and coefficients A and B given in the next table. We can see on these tables the values of coefficients A and B depending on the height of indentations and thicknesses. Eventually, the resistances calculated as defined previously were compared to the results of the testing. The comparisons confirm that, considering indentations as flat elements with a reduced thickness equal to thickness multiplied by ρ, gives results that are safe and coherent with the testing results. For web creeping resistance, it was quite different, because for profiles without embossments and indentations, the calculated web creeping resistance was much lower than the tested one. It confirms the observation highlighted in the literature, showing that the web creeping resistance is different and significantly underestimated compared to the testing results. As a simplification, the web creeping resistance may be determined without considering embossments and indentations. These results have allowed us to submit 2 amendment proposals on Eurocode 313. The first proposal deals with effective section of sheeting with indentations and embossments. It specifies that effective width of a plain wall with embossments indentations should be first calculated according to current Eurocode. In the next step, the indentation or embossment should be taken into account, considering the embossment's indentations as flat elements with reduced thickness. T red is equal to ρ multiplied by T, where ρ is equal to A multiplied by H plus B. H is height of the indentation embossment. A and B are coefficients given before. On these pictures, we can see how the height of embossments and indentations are defined. We can also see the coefficients A and B depending on the height of embossments and indentations and of thicknesses. These proposals also defines the range of validity of the method. The second proposal deals with resistance of sheeting with indentations or embossments to combined bending moment and local load or support reaction. It specifies that resistance moment should be determined considering the indentations and embossments according to the previous proposal, and that the local transverse resistance should be determined without considering the indentations and embossments. For the final part of this presentation, I would like to introduce the Excel files which were implemented to calculate resistances for steel decks with embossments and indentations. These Excel files were developed to provide a reliable design procedure and to encourage and facilitate the use of these products. These files were validated by comparing their results with the results of the testing. Moreover, these calculation methods have been made available to a number of industry users to check their relevance with the purpose. Thanks to these tools, you will be able to calculate span moment resistance and support reaction and moment reaction interaction at the internal support for a profile with embossments and indentations, and one stiffener in the upper flange. You will also be able to calculate span moment resistance end support reaction and moment reaction interaction at internal support for a profile with indentations and with two stiffeners in the upper flange. To conclude, it is important to underline the following points. Firstly, these design by calculation methods were supported, checked and validated by an extensive testing program performed within the GRISP project. Secondly, 4 Excel files were implemented to calculate the resistances of a profile with embossments and indentations. And lastly, these calculation methods were proposed for amendment on Eurocode 313. I hope I have contributed to make you more familiar with these methodologies. I invite you to follow my other talks about steel decks with outward stiffeners, on hold profiles, and on perforated profiles. Thank you for your attention.